Well, good morning and welcome to another installment of Church History Topics. We're going to continue today with talking about more developments in the scientific revolution in the 16th and 17th centuries. This time we're going to focus on medicine, biology, and chemistry. Significant developments in medicine, biology, and chemistry during the period of the 16th and 17th centuries began to reshape how people thought about the physical world that God has made and how man lives in that world. One of the most important developments in this period is the discovery of how blood circulates in the human body by Englishman William Harvey. And on the previous slide, I had a portrait of William Harvey up there. From the time of the ancient Greeks, people believed that the human body was made up of the same fundamental elements that comprise all of the cosmos. The ancient Greeks believed all of the cosmos was made up of fire, water, air, and earth. These elements could have the qualities of being hot, cold, dry, and/or moist. The food and drink that animals consumed consisted of these elements, and in the course of digestion, they were converted into four bodily juices or humors: blood, phlegm, yellow bile, black bile. Now this all sounds very odd to us, doesn't it? But this is how they thought. From these came the descriptors sanguine, phlegmatic, choleric, and melancholic. Hippocrates, Greek practitioner of medicine in early times, 460 to 370 BC, considered the founder of Western medicine, maintained that health required the proper balance of these elements. Imbalance resulted in disease. And I don't know how well you can see on the slide, but this is a diagram that basically helps you understand how people thought about the things that make up the human body and affect the functioning of the human body. But again, it's certainly very different than how we think today. So in a sense, Hippocrates and the school of medicine that followed him can be considered the originators of the notion of homeostasis, or the state of steady internal physical and chemical conditions maintained by living systems. After Hippocrates, the next significant physician was Galen, a Greek who lived from AD 129 to AD 200. Galen perpetuated the tradition of Hippocratic medicine, and he made some advances, but he also regressed in some ways in terms of his understanding of what makes the human body function. Also, in the Middle Ages, the Islamic world had adopted Hippocratic methods and developed new medical technologies. But again, because of separation between Christian Europe and the Islamic Near East and Asia, there weren't too many interchanges of knowledge between these two parts of the world in terms of medicine and science. There was some, but not that much. The son of Aelius Nikon, a wealthy Greek architect with scholarly interests, Galen received a comprehensive education that prepared him for a successful career as a physician and philosopher. And even though Galen was not a Christian, I'm focusing on him because this will help us understand how people thought about how the human body functions during this time period. Born in the ancient city of Pergamon, present-day Bergama, Turkey, Galen traveled extensively, exposing himself to a wide variety of medical theories and discoveries before settling in Rome. He served prominent members of Roman society and eventually was given the position of personal physician to several emperors. His anatomical reports were based mainly on the dissection of monkeys. He later switched to other animals, especially pigs. Now, this is kind of surprising to us. I mean, today, a lot of medical research and biological research focuses on animals and studying how their bodies function. During Galen's time, the reason he had to use animals to discover the human body, in other words, he was trying to make analogies between these animals and how human bodies were constructed and functioned, because there was a prohibition on dissecting humans. It wasn't allowed. And Galen's anatomical reports remain uncontested until 1543. So during all those centuries, through the Middle Ages, into the early modern period, this Greek philosopher-physician, his ideas held sway throughout much of the West. Now, in 1543, a Belgian scientist, Andreas Veselius, printed descriptions and illustrations of human dissections in his work, De Humani Corporis Fabrica. Vesalius is often referred to as the founder of modern human anatomy, and he was able to observe dissections of human bodies, of corpses. And in that time, basically, the way you got a corpse was a criminal who died provided the corpse for your scientific research. So Vesalius was born in Brussels, which was then part of the Habsburg Netherlands. He was a professor at the University of Padua in Italy, and later became imperial physician at the court of Emperor Charles V. This is the same Charles V that dragged Martin Luther before the Diet of Worms to interrogate him about his religious views. So Vesalius is kind of a contemporary of Martin Luther. That will kind of help you place him in history. Vesalius, in contrast to Galen, performed dissection as the primary teaching tool, handling the actual work himself and urging students to perform dissection themselves. So this is a radical new thing that this Belgian scientist is embarking on, to actually cut open human corpses, study them, and then draw the pictures of what is observed. Vesalius considered hands-on direct observation to be the only reliable resource. Vesalius's groundbreaking work, commonly known as the Fabrica of Vesalius, is considered to be a major step in the development of scientific medicine. The book had 273 finely detailed color plates, and the work as a whole gave evidence that the illustrations were the product of actual observation. The Fabrica marks the establishment of anatomy as a modern descriptive science, and Vesalius was only 28 years old at the time the work was published. His work was truly groundbreaking, but it took another scientist to accurately study, describe, document, and explain how the human circulatory system of blood actually worked. Now, if you think about it, why is studying how blood circulates through the human body, why is that so important? Well, if blood doesn't circulate through your body, you're dead. I mean, the Bible itself tells us the life is in the blood. Okay? If you're going to make advances in medicine, in treating sicknesses of human beings, you need to understand fundamentally how the circulatory system actually works. William Harvey was well trained in anatomy, and he, like his forerunner Vesalius, was convinced that the interventricular septum of the heart, in other words, the dividing wall between the heart, the major sections of the heart did not contain any holes or was leaky. Early, philosopher scientists thought, well, the blood is moving back and forth in between the heart. There's holes that it moves through. But he was convinced that this was not the case. In addition, he was born into an era in which experimentation, or the use of the hands, and computation, mathematics, in addition to simple observation, became recognized as essential tools of the scientific method. He was well aware of the work of Copernicus and Kepler, who preceded him, and of his contemporary Galileo. So even though he was studying a very different part of the natural world, in other words, the human body, he wasn't looking through a telescope at the heavens. Nonetheless, the thinking of Galileo and these other scientists affected his thinking in how he approached the study of human anatomy. So for Galileo, the combination of careful observation and computation resulted in nothing less than a switch between the earth and the sun as the center of the universe. Galileo's dictum, measure all that is measurable, and make those things measurable which have hitherto not been measured. This was deeply impressed upon Harvey. But Harvey did not build on anything, revise anything, or improve on anything. Instead, he eradicated an existing dogma without a trace and replaced it with a paradigm whose essential features are immutable. Galen viewed the body as consisting of three connected systems: the brain and nerves, which were responsible for sensation and thought; the heart and arteries, which were responsible for life-giving energy or vital spirit; and the liver and veins, which were responsible for nutrition and growth. According to Galen, blood was formed in the liver from food, carried to that organ from the stomach and intestines via the portal vein. This natural blood then entered the systemic veins and was carried to all parts of the body by an ebb and flow, where it was consumed as a nutrient or was transformed into flesh. So in other words, you eat food, it goes into your digestive system, moves to your liver, is transformed into blood, which then flows throughout the rest of your body, and then it kind of turns into something else. Thus, according to Galen, blood was not conserved. It was constantly being consumed in the periphery, in other words, the remote parts of your bodies, like your fingers or toes. It was constantly being consumed in the periphery and replenished by ingested nutrients or food, and this was all carried out by the right ventricle and great veins of the heart. Harvey's revolutionary conclusion that blood is conserved, in other words, your blood isn't leaving your body somehow and you're not getting new blood directly from food. In other words, it's just circulating through your body. This was based on only a few observations. The major ones were as follows. First, he measured the total amount of blood that could be drained from sheep, pigs, and some other subprimate mammals. He then measured the volume of the left ventricles of the heart of these animals and calculated that if the left ventricle were to empty with each beat, in 1 hour, the total volume of blood pumped would be much greater than in the ingesta, or food, or even that contained in the entire animal. This would be true even if 1/10 of the blood contained by the ventricle were ejected per beat. Harvey's experiments showed that blood did not flow from one side of the heart to the other, as Galen had postulated. Therefore, Harvey concluded, it is a matter of necessity that the blood perform a circuit, that it returns to whence it set out. He also did a direct experiment. He applied a tourniquet to a human arm, the veins became engorged, and that he found that the blood can only be milked from an engorged vein in the oral direction, towards the heart. But when the vein was emptied, it only flowed from the periphery, In other words, from a place far away from the heart. Harvey also asserted that knowing the diameter and length of the cylinder of vein, one can calculate the volume of blood that flows through the vein during rapid emptying and refilling. Harvey showed that in a day, more blood flows through that segment alone than the quantity of food ingested. He proved that the amount of blood in an organism could not be explained by how much food was consumed and how much waste was excreted. Blood was not made directly by the body by eating food and taking in water. Harvey's revolution in anatomy and physiology was set forth in an exquisitely written 70-page monograph entitled Anatomical Essay on the Motion of the Heart and Blood in Animals, commonly referred to as De Motu Cordis, or simply De Motu. It was published in 1628 when Harvey was 50 years old, and it was published in Frankfurt, Germany in Latin, but the first English translation did not appear until 2 decades later, so that for a number of years its readership was limited to the educated population. Nonetheless, in spite of its clear-cut and compelling arguments that were above dispute, the monograph did not bring Harvey immediate fame or prosperity. Like so many scientists and researchers have experienced throughout human history, it was attacked by the academic community, often on the sole grounds that it dared to question Galen and the normal science. In other words, what is the conventional wisdom? So strong was the grip of the authority of antiquity on men's minds. It took over half a century before it was accepted by as distinguished a center of learning as the University of Paris. Indeed, many years had to pass before this immortal work became widely recognized as one of the milestones in human accomplishment. I would also like to note that Harvey did his education at Cambridge, and Cambridge was a center for Puritan thought. Harvey was very much influenced by Puritan Christianity. He was a Christian. Now we're going to turn to some developments in chemistry. Chemistry and its antecedent, alchemy, became an increasingly important aspect of scientific thought in the course of the 16th and 17th centuries. The importance of chemistry is indicated by the range of important scholars who actively engaged in chemical research. Among them were the astronomer Tycho Brahe, the chemical physician Paracelsus, Robert Boyle, Thomas Brown, and physicist and mathematician Isaac Newton. This was a time when, if you were interested in science, you weren't limited to a particular thing that you had to study. Today, when you go into a university, you have to declare a major, you have to specialize in something, and if you're interested in physics, math, chemistry, biology, anatomy, medicine, and all those subjects, well, there's simply too much knowledge in all of those areas. You have to whittle it down. The amount of knowledge and learning that it takes, because of all the advances, people can no longer really be Renaissance men and women as they used to be known. Now, alchemy is an ancient branch of natural philosophy, a philosophical and pre-scientific tradition that was historically practiced throughout Asia, the Muslim world, and Europe. Alchemists attempted to purify, mature, and perfect certain materials. And alchemy, in a sense, you can think of it almost as a branch of magic, or kind of a bridge between magic and science. Common aims were chrysopoeia, the transmutation of base metals like lead into noble metals like gold. They also sought to create an elixir of immortality. In other words, they wanted to create a substance that when you consumed it would guarantee that you would live forever. They also wanted to create panaceas, or kind of medical silver bullets that would be able to cure any disease. The perfection of the human body and the soul was thought to result from the alchemical magnum opus. So people who were doing alchemy were concentrated on what they called the great work. They were in pursuit of a substance that held the very source of life itself. And this was also known as creating or finding the philosopher's stone. Okay, the philosopher's stone, if you've ever, I don't know how many of you read fantasy literature or delved into any of that, but the philosopher's stone is essentially a substance, probably hard, so it's a stone, it's a rock of some sort, that when it is transformed or consumed will guarantee that you will never die, that if you're sick, you'll be made well. So it's definitely, it borders on the occult. I'll just sum it up that way. Whoops. Okay. Islamic and European alchemists developed a basic set of laboratory techniques, theories, and terms, some of which are still in use today. So not everything that happened within alchemy was basically a waste of time. However, they did not abandon the ancient belief that everything is composed of four elements. Again, this goes back to the Greeks, thinking of everything as made up of air, earth, fire, and water. And they tended to guard their work in secrecy, often making use of ciphers and cryptic symbolism. Obviously, if you were in pursuit of the philosopher's stone, if you found it, you would want to make sure nobody else knew that you had, or would not be able to access it. In Europe, the 12th century translations of medieval Islamic works on science and the rediscovering of Aristotelian philosophy gave birth to a flourishing tradition of Latin alchemy that was practiced in Europe. This late medieval tradition of alchemy would go on to play a significant role in the development of early modern science. So one important alchemist was Zosimos of Panaplus. He was a Greco-Egyptian alchemist. He lived lived at the end of the 3rd, beginning of the 4th century AD. His dates aren't totally known. He was a Gnostic mystic, but as you can see from this diagram that's taken from his writings, he invented a distillation process. What do we use distillation for today? All kinds of things. Yeah. all kinds of liquids. Mystical and religious elements within alchemy, as it was practiced in medieval Europe, held back the development of chemistry as a valid field of study and research. And again, in this period, the church is on the hunt for heretics, witches, possibly alchemists. So another reason for secrecy and doing these things behind closed doors. You didn't want the church to find out about this stuff. But social, economic, and educational changes during the Renaissance and Reformation periods helped change the focus of research into physical substances into a true science. Practical attempts to improve the refining of ores and their extraction to smelt metals were an important source of information for early chemists in the 16th century, and among them, Georg Agricola, 1494 to 1555, and his great work, De Re Metallica, not to be confused with the heavy metal band, published in 1556, 1 year after his death. So Agricola was focusing on what you would think of as base metals, but he wasn't focused on trying to transform them into gold or silver. Mostly, he was trying to just figure out ways to make them more useful. Okay, so the focus is beginning to shift. What can we do with these substances that we find in the world around us, and not focus on trying to do something magical with them, but to do something truly useful with them? Agricola's work describes the highly developed and complex processes of mining metal ores, metal extraction, and the state of metallurgy at that time. His approach removed the mysticism associated with the subject, creating the practical base upon which others could build. Unrivaled in its complexity and accuracy, his work served as the standard reference for 2 centuries. Agricola is known as the father of mineralogy and the founder of geology as a scientific discipline. And he was also influential in introducing standardized weights and measures throughout the Holy Roman Empire. Another problem during this time period is nothing is standardized. Galileo wants scientists to measure everything. How are you going to measure stuff if there's no real system of weights and measures? You kind of have to invent that as well. Okay, so during this period, people are beginning to figure out, how do we measure something? How do we measure distance? How do we weigh things? What's an ounce? What's a pound? What's a grain? A grain is something used in pharmacy today. So that was another area of endeavor that needed development. Okay, so now we are going to turn to the very famous Irish Anglo-chemist Robert Boyle. His work was very influential and groundbreaking. He lived from 1627 to 1691. Boyle is considered to have refined the modern scientific method for alchemy and to have separated chemistry further from alchemy. He is largely regarded today as the first modern chemist and therefore one of the founders of modern chemistry and one of the pioneers of modern experimental scientific method. Although Boyle was not the original discoverer, he is best known for Boyle's Law, which he presented in 1662. The law describes the inversely proportional relationship between the absolute pressure and volume of a gas if the temperature is kept constant within a closed system. Over a period of more than 3 decades, Boyle wrote extensively about various properties of matter in all 3 of its basic phases: liquid, solid, and gaseous. He also discussed important aspects of physiology, medicine, the planet Earth, including the oceans and the atmosphere, while contributing key insights to matter theory and the philosophy of science. And really, you should think of Robert Boyle as right up there with Isaac Newton in terms of revolutionizing science in this time period. He was also one of the founders of the modern scientific laboratory, where you conceive an experiment to test a hypothesis, assemble the apparatus and the people needed to carry out the experiment and all the materials, and then publish the results. Boyle's books and articles were in high demand throughout Europe during the scientific revolution. They were often pirated on the continent where his name was recognized everywhere. His writings gave detailed descriptions of his experiments so that others could repeat them. Boyle gave honest reports of exactly what he had done and found, even when the experiment didn't work, a frequent occurrence. Born into a wealthy aristocratic Irish Anglo family, Boyle was so wealthy that later in life he was able to work independently as a scientist without need of a salary or funding from a university. Educated by private tutors, he learned Latin, Greek, French, and Irish or Gaelic, and travel was a part of his education. He went to Florence to meet Galileo, but the great Italian scientist died before Boyle could meet him. Boyle was a devout Anglican, but came to a period in his life when he questioned his faith. He had a conversion experience in Geneva, Switzerland, in the home of a tutor, Isaac Marcombes, a French Huguenot. Marcombes took the adolescent Boyle to church twice weekly and read to him daily from the Bible and Calvin's Catechism. Altogether, young Robin, as his family called him, spent 5 years on the continent with Marcomes, studying rhetoric, logic, mathematics, and the art of fortification, or military engineering, as well as religion. Becoming fluent in French, he traveled extensively in France, Switzerland, and Italy. In 1644, at the age of 17, Boyle's father died, and Boyle returned to England in the middle of the English Civil War. Despite the social and political upheavals in English society, Boyle began working as a scientist at Oxford, although he did not officially join the university. He met Robert Hooke, an Oxford student. Robert Hooke would go on to become himself a very famous scientist. Hooke's extraordinary abilities with mechanical equipment impressed Boyle, who began paying him to work as his laboratory assistant. Now, in 1654, Otto von Guerick had invented the vacuum pump. Boyle learned of this in 1657 and was intrigued. He discussed the concept of a vacuum pump with Hooke, who built one and improved upon von Guerick's design. And they did experiments. They put air into this tube and then sucked out the air, and they took measurements, and they published the results. And this is a graph of his actual results. Now, he didn't actually draw the graph. He just made a table, and the data points that are on the graph appeared in his table. But this is what his data would look like if you graphed it. So reciprocal volume is plotted versus pressure, producing a straight line, an inverse relationship. Boyle and Hooke carried out experiments to investigate the properties of air and the vacuum, making their first great discovery, Boyle's law. And he published this in 1662. With its publication, he emulated his hero Galileo for the first time. Galileo firmly believed that the world could be explained using mathematics, and that's what Boyle began to do. He began to use mathematical equations to explain the relationships that he found in the different phenomena that he studied. And indeed, the ancient Greek Pythagoras had, in a much early age, done the same. Boyle had now shown by experiment that all air follows mathematical laws. Also, Boyle discovered that sound cannot travel through a vacuum. Okay, so he had his assistant, Robert Hooke, construct this contraption that you see pictured here. On top is a glass jar, happened to be 28 liters, the spherical jar. He put a bell inside the jar, and then he rung the bell using a magnet. Hooke had set this up so that the air could be pumped out of the glass jar using that contraption below the jar. They pumped air out of the jar, and the sound of the bell grew fainter and fainter. By turning the handle at the bottom, Boyle or Hooke could pump air out of the glass jar at the top. Take air out, put air in, what happens to the sound of the bell? Now today, we talk about sound waves. So what are Boyle and Hooke beginning to discover? Sound has to travel through air, otherwise you can't hear it. And later scientists would discover that it moves in a wave pattern. Obviously, in performing this experiment, Boyle also showed that magnetic forces can travel through a vacuum. Otherwise, he could not have rung the bell. And I think you can begin to see how these ideas might have application in astronomy. Although not fully appreciated at the time, this was a highly significant moment in science. Bell had shown that physical forces could be transmitted across a vacuum. Furthermore, he showed light can travel through a vacuum because when air was pumped out of the jar, everything in the jar remained perfectly visible. Using a candle, Boyle showed that a vacuum will not support combustion. So he therefore also found that only part of the air supports combustion. He thought it was a very small part. But at this stage, none of the elements that make up air had been discovered. Oxygen's discovery lay over 100 years in the future. Boyle also showed that air has weight, although this had previously been shown in 1644 by Evangelista Torricelli and seems to have been known by Empedocles 21 years earlier in ancient Greece. But what's good about this is Boyle's work is beginning to tie together different areas of science, and because he's proving these concepts in a laboratory under controlled conditions that can be replicated by other scientists, he's establishing truths that can be built upon. Published in 1661, Boyle's work, The Skeptical Chemist, was a turning point in chemistry. At the heart of Boyle's ambition for chemistry lay once again Galileo's idea that the world could be understood through mathematics. And Boyle wished to turn chemistry into a quantitative science. And of course, today we know that that happened. He was successful in that. Just as Galileo had rejected Aristotle's theory of motion of the planets, Boyle now rejected the Aristotelian elements, earth, water, air, and fire. He also rejected the Greek Paracelsus's principles of salt, sulfur, and mercury. Boyle correctly defined elements as simple substances that could not be decomposed into other substances. But Boyle was not able to find an experimental method to prove whether a substance was an element or not. It would be more than a century before the French chemist Antoine Lavoisier broke through this experimental barrier and produced the first list of chemical elements. Boyle believed, along with other scientists, both ancient and modern, in the atom, the smallest unit of ordinary matter that forms a chemical element. Although he denounced mysticism, Boyle remained an alchemist, believing that one element could be transmuted or changed into another. He thought, correctly as it turned out, that this could be achieved through a rearrangement of the basic particles making up the element, but it would be almost 300 years before this was first achieved. Ernest Rutherford, a New Zealand scientist, transformed nitrogen into oxygen in 1919, the first instance of a transmutation that the alchemists had hoped to achieve. Boyle's activities included much besides scientific inquiries. He actively supported charities and anonymously gave enormous sums of money and medicines to the poor, starting first with the tenants on his estate. He supported efforts to translate the Bible into Native American languages and into Welsh, Irish, Turkish, and Malayan. He was strongly opposed to religious persecution in a time when Catholic and Protestant nations alike spent blood and treasure on religious wars nearly constantly. Well, that concludes my presentation of developments in medicine, biology, and chemistry. Any questions or comments? So, you can, again, I'm glad to email the PowerPoint to you if you would like that. If you want a printed copy, I can make you a printed copy. There's a lot of stuff here you could study on your own. You can learn more about Boyle. You can learn more about these other scientists. Early developments in medicine are always interesting. Christiana?
Can you go into a little bit why all of the scientific discoveries and things going on, why that's so relevant to church history?
Again, many of the people doing these activities are Christians themselves, not all, but many of them are sincere, devout Christians, and they believe, and they might not have articulated it this way, but certainly at some point they probably would have realized God had blessed them with intellectual gifts and talents, and God has made a world that man is to take dominion over fundamentally. And one way that man can take dominion over the world that God has created is to understand it, understand how it functions, and be able to take hold of it and doing things like experiments and testing and cutting open cadavers and studying them and conducting scientific experiments in a laboratory, taking the different aspects of the world that God has created, taking hold of them, seeing how they function, explaining how they function. And in so doing, certainly one aspect of this, especially when we think of medicine and biology, is if we understand the human body better and we understand how it functions, maybe we can do a better job of helping people get well when their body is not functioning as it should be, So, obviously medicine is a direct application of the dominion mandate, I think. This is an area where, by the grace of God and the intellectual gifts and talents that He gives to human beings, we can learn about illnesses, how they affect us. We can learn about different therapies. Obviously, in the course of that, some discoveries proved not to be very fruitful. Other things proved to be, the history of medicine is filled with instances of substances and things that were used as drugs that turned out to be very harmful. But, in the area of chemistry, that's another thing. We know so much more now about different substances that, we've created. For example, pesticides and other poisons, they have some beneficial effects. For example, we can spray DDT in the environment, eradicate mosquitoes, get rid of malaria. Great. But then all the birds die and other animals die, and now we have this poisonous substance in our environment that we now have to deal with. So, everything that man does probably has an unintended consequence as well as sometimes the hoped-for consequence. But certainly God has given us these things. And again, this is more of a Christian perspective. The idea that man can lay hold of God's creation, learn about it, understand it, and then begin to change it, hopefully in the right direction. Some, not always. That's part of the dominion mandate. Byron?
Can you talk a little bit about where bloodletting, how it was?
Yeah. I'm sure Liz Brewer would love to field this question. Yeah, the idea, so going back to the idea of the bodily humors, the phlegm, the yellow bile, the black bile, and I don't know a whole lot about this stuff, just a little bit, but the idea is if you're sick, maybe you've got too much black bile, or maybe you've got too much phlegm, so we have to get rid of it. And what's the easiest thing to take out of the human body? It's blood. And I guess the idea was, they assumed these substances were in our blood, and by bloodletting, that would take care of the problem. Now, the interesting, I've found this very interesting, but bloodletting is not, there are occasions where it is still used in modern medicine. There are still valid applications for it. And if you want to talk to someone who specializes in wound care, you'll get some interesting insights about that, which I won't go into. Snake bites, treating snake bites, yeah, bloodletting is useful in that. Yep, John?
It seemed like Robert Boyle and Isaac Newton were both really influential scientists of their time, really
Yeah.
revolutionary. What do you think made Isaac Newton that much more widely known? Because like even when I was in school, we were about Isaac Newton all the time, mathematician, but you didn't really hear of Robert Boyle that much.
Yeah, unless you take a class in chemistry, you're not really going to know much about him. And I took chemistry in high school, and I never really knew that much about him, but, we were mostly mixing substances in the laboratory and blowing things up. I had very exciting high school chemistry. I guess, you'd probably get different answers. If you talk to a professor of physics, you'd probably get a very long, involved, and thorough answer. My brief answer is, if you want to study physics today in an American high school or college as an undergraduate, what you are going to study is Newton's. What they lay out is basically Newton's body of work in terms of the theory of motion and it's all Newtonian physics is what you learn when you take a physics class in high school or college at the undergraduate level. There's quantum mechanics, there's areas of physics that are difficult to access for the average student. So Newtonian physics is pretty easy to understand. I mean, it's not easy, but relatively speaking, it's pretty easy to understand. And because Newton developed the calculus, a branch of mathematics known as calculus, if you study calculus and along with that trigonometry, you're going to be able to understand Newtonian physics pretty easily. So, Sid?
Well, there weren't all my friends with Galen early. For example, if you do that, you can actually, that's why they invented the nuclear bomb. So you can avoid the sub-elements. But it's interesting because, as you mentioned, modern problems is there's not as one solution. I mean, like, one area I'd love to see more development will be, ironically, recycling technology.
Yep.
It's not like recycle, it's truly recyclable.
So, I guess I would just summarize by saying, for us as Christians, we should have a view of science. Number one, it's not inherently evil. It's not inherently good. It's what people do with it. It's a branch of, or an area of study where really what we need is more Christian involvement, not less. We need more Christians who are focusing on developing scientific methods, understanding of natural phenomena, and doing work that says, okay, and obviously at this point we could depart into the whole, creation versus evolution thing. That's a whole nother thing. But again, keep in mind, what I want to focus on is science. In science, you have hypotheses that you test. Neither creation nor evolution is subject to the scientific method, despite what a lot of scientists will tell you. We cannot set up laboratory experiments to test the beginning of the universe. It's just not possible. But in those areas in which the scientific method is appropriate, we need more Christian scientists advancing knowledge for the benefit, really, of all human beings. When you think of the number of Christians involved in medicine, again, that's an area, where we can see direct application, where it truly makes sense as a Christian to work in that field, advancing medical knowledge and science so that we can have better drugs, so that we can have better therapeutic techniques to help sick people get well. And of course, many Christians have focused on that area, but we need Christian chemists, we need Christian physicists, we need Christian botanists, we need Christian ecologists. The earth is the Lord's, but he's given it to man to rule in. We need to rule well. And I think Christian scientists can bring that part to their scientific work and do a better job, hopefully. All right, well, let's break so you have a chance to grab a coffee.